Hello everyone, welcome to the Math Tablet. In this session we're having a look at basic differentiation. If we have a function y that looks like the form ax to the power of n, then the gradient function, often denoted as dy dx, is equal to a times n times x to the power of n minus 1. So to help ourselves remember that, we think of it as multiply the coefficient to the power and reduce the power by 1. So let's have a look at some examples. Suppose I have y equals 10 times x to the power 5. Okay? To find the gradient function then, dy dx, or the derivative, I will multiply the 10 and the 5, giving me 50, and then reduce the power by 1, so I have x to the power of 4. Let's have a look at one more example. Suppose I have y equals x squared over 6. Now, some people like to think of this as 1/6 times x squared. It is definitely the same term, but what it does is helps us isolate that coefficient from the actual term. So to get the gradient function then, dy dx, we can multiply the 2 and the 1/6, giving me 1/3, then reduce the power by 1, which is x to the power of 1 here, and because x to the power of 1 is really just x, I can write this in a more simplified way as x over 3. Now sometimes we can incorporate our index rules as well. So suppose I've got y equals 7 times the square root of x. Now I can think of this as 7 times x to the power of a half. So before I differentiate it, or find the gradient function, what I've done is rewrite that term such that x looks like x to the power of a half. It just helps us isolate that power then. Dy dx will be 7 times a half, which is 7 over 2, and then x to the power of 1/2 minus 1 is -1/2. And I can use my index rules again to make this into a simpler form. 7 over 2 times x to the power of a half, and I could even then write it as 7 over 2 times square root of x. Another case where we often use our index rules is something like this. So y equals, say, 4 over x. Before we differentiate it, or before we find its gradient function, we would write this as 4 times x to the power of -1. Okay, and then to find dy dx, to find the derivative, we would go 4 times -1, giving us -4, and then reduce the power by 1, x to the power of -2, so that becomes -4 over x squared if I'm asked to leave it with a positive power. Let's have a look at something like y equals 8. Now we can think of this as 8 times x to the power of 0, okay, because x to the power of 0 is 1, isn't it? Now the gradient function then, dy dx, would be 8 times 0, which is 0, and then x to the power of -1. Now 0 times anything will just be 0, so your gradient function dy dx is going to be 0. Now that is in fact true of any function that looks like the form y equals a constant, and that is because graphically, if we've got a function y equals a constant, it's going to be a horizontal line, isn't it? Which means that its gradient is 0. So it makes sense that the derivative dy dx works out to be 0 whenever we've got a function that looks like y equals a constant. Now let's have a look at just a variation on this type of function as well. let's suppose we have something like y equals 9x cubed minus 2x. So notice that we've got two terms here. To find the derivative, very simply, we differentiate each of those terms individually. So the first one, I would multiply the 9 and the 3, giving me 27, and then x squared. And then the second one, I'm thinking of the x as x to the power of 1. Okay, so I've got negative 2 times 1 giving me negative 2, and then x to the power of 0, isn't it? Which means it's actually 27 x squared and then minus 2, because x to the power of 0 will give me 1. Now just one thing in regards to notation, I've mainly used dy dx in terms of finding the gradient function or finding the derivative. Sometimes it can also be expressed with just a dash, so y dash would have the same meaning as dy dx.